Great. Thanks, Marion, and thank you very much to the organisers, both for Marion and the organisational team, both for the invitation and the excellent day yesterday. I think the discussions were really illuminating and exciting, and actually it's caused me to rewrite most of my talk on the train home last night. So apologies if it's a little bit stilted and a bit slow. This is the first time I've done this in this format, so we'll see how it goes. Yeah, I'm Matt Anson. I'm a technical lead at Stack HPC. I'm going to talk today about particularly high performance hardware or networking hardware, and how Stack HPC envisages that working in the cloud, particularly in science communities. I think generally this talk fits into the Bayes 2 second work package, which is the co-design package. But there are some other bits that I've tried to relate to other parts of the Bayes 2 project as well. So do the important things at the start. So there's lots of this work, or in fact all of this work, is supported by communities, many of which are in the room and on the call today. So this is a joint effort. We have contributions we have funding contributions, we have contributions of infrastructure for continuous integration, and most importantly, from these institutions and partners, we have ideas and feature requests and all of those things that help make the stuff that we're doing at Stack HPC useful to the communities that are with us today. So I do the bit of marketing as well, to give an overview of Stack HPC. We were formed in 2016. We're based in Bristol. I've been with the company almost 2 years. We have a presence across the south of England, so Oxford, Cambridge, and Bristol, and then also in France and Poland. We employ around 25 people. Our background is HPC, software-defined networking, systems integration, that kind of thing. But we do quite a lot of OpenStack development and operations now, and we're trying to grow our staff in the AI and ML space, and we're trying to move this expertise in AI and ML into the cloud to address these questions around experiences around HPC and high performance data analytics. All the work we do is open. It's done in an open source way with permissive Apache 2 licenses. We engage very much with the upstream OpenStack community, and we're part of the scientific working group in the Open Infrastructure Foundation. And we're beginning to focus more on hybrid cloud enablement, so being able to take your on-premise cloud, your workloads on your on-premise cloud, and burst them onto other clouds that may or may not exist. So that's the sort of marketing bit over, and the rest of the talk isn't really a marketing pitch, though I've got a new book out if anyone's interested. It's a bit more of a description of some of the specific technologies that are in Stack HPC's wheelhouse, and ones that I felt aligned with the Bayes 2 mission. And as I said, apologies if this is a bit unpolished. I sort of rewritten it after we discussed yesterday on the train home. And really this talk is about how can we propagate high performance hardware from the metal, so the bare infrastructure, up to particularly Kubernetes-based science platforms. So cover this with a couple of points. The why, I guess, as an introduction, why you use OpenStack, why you use Kubernetes, and why we're interested in RDMA. Then talk very briefly about the nuts and bolts of how all that works, and then go on to talk about using Azimuth, which is Stack HPC's interface for building platforms on, or science enabling platforms on the cloud. So to start, why OpenStack and why Kubernetes? And based on discussions yesterday, I thought I'd do a brief introduction to what is OpenStack and what is Kubernetes, and why they are important. So OpenStack is a way of orchestrating a private cloud or an on-premise cloud. Many of the organizations in the room have one of these, some of which we support, some of which we don't. Please feel free to email me. And the blurb from the OpenStack website says, OpenStack controls large pools of compute, storage, and networking resources, and manages them through an API. And I think I can condense that down to say that OpenStack is an API for controlling quantities of hardware, whether that be servers or networking or storage. Kubernetes, on the other hand, is an open source system for automating the deployment, scaling, and management of containers and containerized applications, and can kind of characterize that as a distributed container operating system. So it lives on many servers. You can install packages onto it, which are made up of many containers, and they may live across many hosts. And it has its own abstractions over networking, storage, and scheduling. And you commonly run Kubernetes on virtual machines on a cloud. That might be OpenStack, or it might be the one that belongs to Google or Amazon. And really, this is condensed down to an API for controlling containers. So this graphic in the bottom right is more or less how I see this working. You have a bare metal server, you have an OpenStack instance or virtual machine that lives on that server. You have Kubernetes in that virtual machine, and then you have a container in your Kubernetes. So many layers. So why are these important? As we see increasing diversity in user requirements, particularly in the science community, even when I was working in science, we were beginning to see grants that were funded to build a web application to serve a database to your community, which has different requirements to somebody that wants to run a simulation on an HPC system, and again, similar different requirements to somebody that has that wants to run AI or something like that, or big data. And really, everybody wants their own slice of the pizza. So to take infrastructure and carve it up into a pizza, and you should have the pizza slice that you're given, and you should enjoy it. And what Stack HPC desires to do is to move away from the pizza model to the reconfigurable conference room model, which is a bit of a jarring segue. But the idea is that you can reconfigure your infrastructure such that you can have the same servers participating in one big room for one big conference, or you can have the same servers and networking participating in many smaller conferences with isolation in between them, represented by these movable walls. So this is the sort of traditional approach where you would procure some HPC hardware to run your HPC workloads, you procure some big data hardware to run your big data workloads, and you procure some deep learning hardware to run your AI workloads on. Each of these would have their own specific orchestration on top of them. You talk to Slurm for HPC, you use Hadoop or something like that for big data, and to be honest, you might use Kubernetes for deep learning or something else. But what the vision is, what Stack HPC's vision is, that we end up with this pool of shared configurable hardware that's managed with OpenStack and Kubernetes, and then each of the workloads on top of that are able to talk to a consistent set of APIs to provision the infrastructure that they need. And actually, as we said, I think Paul said yesterday, the lines between the requirements of these workloads are becoming much more blurred now. The hyperscalers want or the traditional playground for the AI and deep learning is the hyperscalers, and they want the HPC interconnects. The AI and deep learning people want to do stuff on HPC, particularly with the large language models and training and that sort of stuff. So actually, this top section here is starting to become much more fluid. So that's the background of the infrastructure. I'm going to talk a little bit about high performance networking now, and why you would want to use it. So high performance networking, put simply, also using RDMA over instead of TCP, makes your distributed codes run faster. They run with lower latency and greater interprocess bandwidth. And actually, this comes back to a point I think made by Jeremy yesterday, that running your codes slightly faster is as an important improvement metric as running bigger models in the exascale world. So access to this high performance hardware is really important. So this is OpenFOAM, which is a fluid dynamics simulation, and you can see that all of the this is wall time on the y-axis, and you can see that all of the RDMA transports have much lower wall time than the TCP-based ones. So that's just an indicator of why you might want to use some high-performance hardware. You can see this when you're looking at MPI. So if you send small messages, you get much lower latency with the RDMA transport. If you send large messages, you get much higher bandwidth with the RDMA transport compared to the TCP here. So this work was, these benchmarks were done in partnership with NVIDIA, and we produced a set of tools called KubePerf and I've added this slide in because I think it relates quite nicely to Jayan's work on work package 1 of Bayes 2, which is the ML Commons and the ML benchmarking suite. This is slightly different, maybe complementary, in the sense that this is a set of Kubernetes tools that do performance analysis on a Kubernetes cluster. They run bandwidth, IO benchmarking, that kind of stuff, and it allows you to investigate how your underlying infrastructure works, how well your underlying infrastructure works. We have a repository for it, and we would love to incorporate some of the ML benchmarks from the Jayan's team in this. So the next stage is how do we get RDMA into Kubernetes? So Loki is Linux OpenStack Kubernetes infrastructure. How do we get RDMA all the way from the bare metal server up into Kubernetes pods? And the short answer is it's quite hard. And unless you're a real ops enthusiast, this slide kind of summarizes all that you need to know about this. In the interest of time, I'm going to shoot through it quite quickly, but the important thing to remember is that because of our reconfigurable conference room infrastructure, each of our bare metal servers may host many OpenStack virtual machines in the dark gray here, which may belong to different tenants doing different workloads. So this machine might be a HPC node. This guy is running Kubernetes and has many pods on it. And the difficulty or the challenge is being able to propagate high performance networking from the bare metal into each of these individual Kubernetes pods, and also into this HPC compute node, for example. So it's handled at three levels really. So we use Color Ansible, which is an OpenStack project, to configure RDMA access inside the OpenStack server. We use Azimuth to configure Kubernetes clusters that have access to RDMA, and we use Azimuth to configure RDMA inside Kubernetes pods. So as I say, the nuts and bolts of the Loki process they require some in-depth knowledge of how all that stuff works, and we shouldn't really expect scientists to be able to understand that or have to understand that to be able to get their work done. So this is why we developed Azimuth, which is a web interface for scientists that talks to both OpenStack and Kubernetes. It allows you to provision a Kubernetes cluster or another type of science enabling platform like Slurm, or just a machine with a desktop, and it allows you to provision those on OpenStack. The science platforms that they deploy, so the Slurm or Kubernetes, contains all of our knowledge for best practice around performance and security, and it allows you to abstract away knowing anything about the underlying infrastructure. And specifically in this case, it allows users to get hold of RDMA or GPU-enabled Kubernetes on their institutional OpenStack cloud with just a few button clicks. So the web interface looks like this. We present a series of platforms that you're able to launch with a single click. So they may be Kubernetes, they may be, as I said, a workstation, or they might be a whole Slurm cluster, which we deploy with Terraform and Ansible. You can pick a few options, such as what version of Kubernetes you want to run, how big you want your Kubernetes control plane to be, how many nodes you want to have in your Kubernetes cluster, and then you just click the button and you end up with a Kubernetes, a high performance enabled Kubernetes cluster. We can install applications directly onto Kubernetes cluster. So Dask is the sort of canonical distributed ML environment, if you like, that will run on, that we have an installer for Kubernetes. Each of the, if a platform has a web interface, once you've launched it, you can click your web interface to travel to it. So this particular Kubernetes has a Jupyter Notebook running on it. You can click that and you'll be directed straight to it. This Slurm has Open On Demand running on it, and you can see each of these has a monitoring stack installed on it. And you don't just get Kubernetes when you launch one, you get Kubernetes, as I say, with best practice. So you automatically get monitoring and logging, you get GPU drivers, you get high performance networking drivers all built in, and you don't have to worry about how any of those work. So not really talking about Slurm here, but you can also deploy a Slurm cluster if you want to. It means that you don't have to wait for others on the big queue, and you can be in control of your own Slurm cluster. Skip through this one, and then the final thing is that we could do a GPU-enabled kubeflow. So kubeflow is an MLOps platform, and you automatically get access to any GPUs that are configured in your cluster, which is quite nice. And yeah, we can do some stable diffusion and how we can generate a picture of an astronaut riding a horse, which is always fun. So we have a few things on our roadmap. In the interest of time, I won't go into them in much detail. Basically, we're really interested in how to do hybrid cloud. So having remote partitions, Slurm partitions on somebody else's cloud, how to manage Kubernetes on somebody else's cloud. We are really interested in storage that you can keep around for a long time, and also integration with things like Rusio for transferring data on demand into your platforms. So to summarize, OpenStack and Kubernetes, we see this as ways to break down hardware silos. RDMA makes your distributed codes run faster, but getting RDMA from the bare metal up into Kubernetes pods is complex, and actually you guys shouldn't need to know about that. We should leave that to the ops people to abstract away the complexity there. And we do that with Azimuth, which allows us to create science platforms on OpenStack that use available high performance hardware, are secure and follow best practice, and they don't require specialist knowledge of infrastructure. It just works. So we have a few ways to get involved. You can try Azimuth, you can install it onto your OpenStack cloud. Please have a look at kubeperftest if you're interested in performance benchmarking your Kubernetes cluster. And we occasionally blog about things to do with Azimuth. So visit our website, read our blog, get in touch. Thank you very much. And this is somebody else's slide.
Thanks, Matt. So we're running